Go ahead.
Yeah, first let me thank the organizers for inviting me to give an advertisement here for actually why do we need more complex models than slab models. So I really enjoyed the previous talk by Matt Richter, where he said, well, you know, in some cases we need to do the hard thing, namely do the radiative transfer. And so in this presentation, I would like to convince you that this is really absolutely needed. And I think especially with all the wonderful data that we expect to get, both from ground-based, also from space-based instruments in the future, I do think we really should make best use of it and really look at it with the best modeling that we can also produce. So let's see. Yes, this moves. So in fact, what we see, and this is something that Matt already hinted at, in these planet-forming disks around young stars, gas and dust are actually very closely intertwined, and this is not only by radiative transfer, and they cannot be understood independent of each other. And I would like to take the next almost 20 minutes to convince you that this is really the case. But just to give you a couple of pieces of evidence, there has been a very nice paper by Yao Liu that showed that actually water lines in these planet-forming disks do produce a quasi-continuum. And so if you have your observations where really you have no idea where the continuum is, you need to figure out a way to tackle the continuum together with the mid-infrared lines, because otherwise your line interpretation may go wrong. Also, what we showed in recent work is that the dust opacities affect the strength of these mid-infrared lines. And this is exactly what Matt showed for this hot star AFGL something, where they actually figured out that the lines are not as strong as they would expect from a slab model, because it is the dust opacity that limits how deep you can look into these disks. And so it is important to actually have a good understanding for what kind of dust you have, what kind of temperatures does the dust have in order to interpret your line emission. And then last but not least, if we look purely at the physics going on in these disks, there's a lot of discussion now from the ALMA observations, because we see dust substructure, we see the dust settling to the midplane, we also see radial migration of dust. But I would like to recall that all of that happens because of the presence of gas. There is a gas pressure in this disk, and depending on how the gas pressure changes, as a function of radius, for example, your dust is migrating or being captured in dust traps or whatnot. And so it is actually important to not do your interpretation of data without actually taking the other phase into account. And last but not least, of course, we all know that chemistry is actually coupling the two very well, because it is the very small dust grains on which the ices are freezing out from the gas. And so we get icy dust. So on the right-hand side, you see actually a picture of such a planet-forming disk, and it shows you what kind of unique diagnostic you get all the way from the inner to the outer disk if we have full access to the near-infrared, the mid-infrared, the far-infrared, and the sub-millimeter. So all of them really bear very important diagnostics. And I think it is only through having the complete picture from all these wavelength ranges that we get a good idea about what these disks really are and how they are forming planets. So let me give you an example for what I mean by this modeling. This is one particular code I'm showing here on the right-hand side, that we actually need a framework for how we want to study these disks. They are intrinsically 2D or now even 3-dimensional structures, because we can spatially resolve them. But in general, what we have is a density distribution for gas and dust. We need to do the radiative transfer depending on that density distribution. And then based on the dust temperatures that we can find in that way, given certain dust opacities, we can understand the chemistry that is going on at each point in the disk. And we can solve also the heating and cooling balance for the gas to get the gas temperature. And with all of that, we can get all the observables we want, whether it's a spectral energy distribution or a line profile, and compare that to the observations. The advantage of doing it in one go within one single model is that we try to capture as much of these intertwined processes between gas and dust self-consistently. So of course, the radiative transfer matters. The way how you distribute your dust opacities will determine how heating radiation is penetrating into the disk, and it will have an effect on the gas temperature as well, which then affects the gas emission line. And so I show here one example, which is the disk MWC480, one of the disks we modeled within the Diana project. And that was a big European project that got funded in the FP7 program in order to develop a framework with which we can really study these disks using all the data that is out there from the UV or X-rays even all the way to the sub-millimeter, and try to understand them within one single modeling framework. And so what we did in that particular project is we did SED models for 27 objects that are very well-studied disks, and also 2D gas plus dust disk models for 14 objects. So if you want to know which objects these are, I would advise you to have a look at the Diana database, which contains all these objects observationally, but also from the modeling side. And I want to make clear that, it's not only one model that can do this. I mean, there are several codes out there that work in the same way, codes by Simon Bruderer, Ted Bergin, Ilse Cleaves, Uma Gorty. So all these codes work in this way, that they try to come up with a coherent picture of what gas and dust are doing in order to interpret a multitude of observations. So let me build on this. Of course, you can say, well, nowadays we know that these disks have substructure, and that's true. This is not what we were capturing in these Diana models, but this is an example of how we actually went to the next step. Because in the end, the substructure that we see is often a small modulation of what we thought a smooth disk model would look like. And you see it here. So we used the D-Sharp data from Andrea Isella's paper, and we actually modulated our dust surface density in such a way that it actually matches the dust emission that has been seen for this object. So the kind of rings and gaps in this disk. And what we were interested in is trying to assess whether or not the gas also shows gaps or not. And the most important message, and this is really only something you can learn when you do the full gas plus dust modeling, the thing that we learn is that the dust opacity is important here, because it matters whether you are in a gap or in a ring, because if you're in a ring and you have a lot of material there, you block the view of the backside of the disk. And so what the D-Sharp project showed from the ALMA observations is that the CO lines also have a modulation like the dust modulation. But this modulation, in fact, comes partly also because within the gaps, we actually see the backside of the disk. And so we get more CO emission out. So in a sense, what we learned from gas plus dust disk modeling is the temperature changes of the gas, because we introduced gaps, of course, but there's also an opacity effect. And part of it, so the temperature effect has already been published by Nienke van der Mare in similar type of models. And we show here that actually the opacity is also very important. And what we see on the bottom row, you see the channel maps, on the left, the observed, and on the right, different types of models where we only introduce dust gaps, or we also introduce dust plus gas gaps. And you see clearly, if we deplete the gas in the same way as the dust, we would overpredict this kind of little substructure that we see in the channel maps with respect to observations. So either there are no gas gaps, or maybe there are small gas gaps. But again, the bottom line is we have wonderful data. In this case, it's from the ALMA Observatory. But it really warrants to have very detailed models that connect the radiative transfer plus opacities and all of this in order to come to the right conclusion. We have taken this one step further. Of course, HD163296 is a disk for which both Christoph Berndt and also Richard Teague already proposed that there are multiple planets in there. So what if we have actually a gas giant planet forming in such a disk, and then it is maybe surrounded by its own circumplanetary disk that could do moon formation, or that still leads to accumulation of more mass in the planet? And so we have taken the same concept of these disk models, gas plus dust disk modeling, and applied it to a system where we have wide orbit planetary mass or brown dwarf companions. And this is an example. This is CT-Char B, which has a companion, maybe brown dwarf mass. And we can simulate what the disk around such a wide orbit separation planetary mass companion would look like. And that's what you see in the middle panel. There will be scattered light image. I blocked that because it's not yet published. It is a sphere image, not the NACO image that you see here, but it's detected in scattered light. But we also show that there's prospect to see this disk, for example, in CO with ALMA. And we can see the channel maps. We need very deep ALMA observations, but we can see the channel maps, and then we can kinematically measure the mass of this wide orbit separation companion. And more importantly, we also got a JWST proposal approved, because with these simulations, we can show that actually with the sensitivity of Miriam space, we will be able to detect the emission both from the dust and the gas if there is a circumplanetary disk around this object. And so this is really very cool prospect. And taking this even one step further, of course, people are looking for these young planets that are forming in these disks. And one study that has been done recently is a VISIR near study by Dominique Petit-de-la-Roche. And they have taken these kind of, at the moment, these are the deepest resolved mid-infrared images with this near system that has been on the telescope only for some time. And they tried to look for these planetary mass companions with these images. And in fact, what you see here is the observation on the left-hand side and the model on the right-hand side. So there's fairly good agreement, but you also see that there are no extra sources detected. And so in order to put mass limits on what we actually can rule out as a planetary mass companion, we have run these models again for planets plus a circumplanetary disk around them in these different filters that VISIR has observed, in order to show that, for example, in this particular case for HD100-546, there is no wide orbit planetary companion. And a similar analysis has also been presented in the paper by her for TW Hydra, HD169-142 and HD100-543. However, this is VISIR, but we will get METIS eventually. And so this brings us to the point that these planets with their circumplanetary disks may not only be a source of continuum radiation, but they can also have line radiation. If you have CO molecules in these circumplanetary disks, and our models with the chemistry and radiative transfer predict that we should be able to see the CO emission from these circumplanetary disks, then we can take the full advantage of METIS at a wavelength of 4.7 micron, where it detects the CO raw vibrational emission, because now our planet is actually shifted in radial velocity with respect to the emission we see from the protoplanetary or planet-forming disk. And so we see the CO emission from that circumplanetary disk in one specific channel. So what we get is, instead of ALMA CO channel maps, we will get channel maps with METIS in the mid-infrared. And this is extremely powerful. So what you see here is a simulation of one particular planet, again in the system HD100-546, that we placed in the inner cavity, and we clearly see the signal in the channel of 12 kilometers per second to the upper left here. And so that is the prospect, that we can really go into characterizing the material that sits in these circumplanetary disks. And second to last, I would like to convince you that we can also use these different images that we get from these planet-forming disks in order to measure, in this particular case, the mass of a circumplanetary disk. So this is one particular system, it's PDS-70, and there are very nice ALMA observations at long wavelengths, plus a sphere Q-phi image by Miriam Kepler. And we did the full radiative transfer modeling in the near infrared, but also at sub-millimeter wavelengths, to come up with a coherent and consistent dust model for this particular source. And there's a little smudge in the upper left ALMA picture, which is a tiny little bit of emission at the position of the planet PDS-70c, which has been attributed to a material sitting there in a circumplanetary disk. And so with the help of this full radiative transfer model, we could actually not only check what is the temperature of such a circumplanetary disk if it sits embedded in a planet-forming disk, where it's illuminated not only by its own planet, but also by the material from the circumstellar disk around it and by stellar photons. And you need the full complexity of such a model in order to be able to, in order to be able to tie a mass estimate to this submillimeter detection of the circumplanetary disk. And so we did that using the typical planet parameters that have been estimated also from H-alpha observations. And what we find is that this circumplanetary disk has a mass of the order of 0.7 Earth masses or less. And this is enough to form a moon system like around Jupiter, for example. So last but not least, I would like to use this also for some advertisement, because I think, yes, we will be getting great instruments in the future. And one of them I showed specifically, ELT METIS. But I think there are lots of things that we still don't know, even after METIS will come online on the telescope. And there are very unique diagnostics in the infrared that at the moment we miss, and we have no way of getting any time in the near future, except if some of the smaller probe or M-class mission concepts go through. So for example, how do we actually measure disk masses? And in the view of time, let me switch the picture to a different one. What we actually need is have access to the HD lines at 112 and 56 micron so that we can study the disk gas masses in large statistical samples of planet-forming disks. And at the same time, also, again, we need far infrared observations to follow HD, water, OH, all the way from the planet-forming disks into the debris disk phase. If we get line profiles, this is what Matt Richter also highlighted, if we get high spectral resolution in space, we have access to the spectral line profiles of H2, OH, iron lines. We can study the wind and the gas dispersal in these systems, something that we cannot do from the ground easily, because in space we really have a factor 1,000 or so higher sensitivity. And what we also get in the far infrared is not only the mineralogy of dust, so see calcites, hydrosilicates, and connect to solar system bodies, but we also have access to thermal emission of ices at 45 and 63 micron. So to study actually how the ices evolve, because ices are very important also in the buildup of planets. And so I'm going to end here and just say, I really liked your introduction, because these are also my two favorite images from the last month. And I think it's great to see that JWST is doing wonderful at the moment. And I'm very much looking forward to all the data we get. And I think it will keep us busy for many years. Thank you.
All right, thank you for the very nice talk, Inga. All right, so any questions for Inga? So again, please feel free to raise your hands in Zoom, or ask your questions in the Slack channel. And so again, it's psi, YSOs, disks, star formation. So right now we actually have a question from Leo. He says, hi Inga, I'm not sure I understand your comments, only made on the slide with the near image, that METIS will be only 10 times more sensitive. Is that compared to ALMA CO maps, and specifically for warm CO?
No, I think METIS will be 10 times more sensitive in these continuum images than VISIR near. That was the calculation. The VISIR near system is already more sensitive, say, than the normal VISIR instrument on the VLT. And I think in terms of continuum sensitivity, METIS will then have 10 times better sensitivity for these point sources to see these little planets that may be there. That is the point. We can debate that number. And I'm pretty sure Dominique knows much more about it than I do, because it has been her paper.
Yeah, I'm not quite sure that that can be correct. I mean, the point source sensitivity of METIS is a lot better than near, but I'll send you a number in Slack and then we can discuss it.
Okay.
All right, so we have a question from Mikako Matsura. She has two questions actually. So one of them is on HD 100-546. And the question is, what is the extinction excitation temperature of CO at near infrared. And then her second question is, could you explain why HD is so important?
Okay, so the excitation temperature, I mean, typically for these CO low vibrational lines, the excitation temperature is of the order of 500 to 1000 Kelvin. Yeah, so it's very hot CO gas, and the gas is hot and it is excited both because it sits very close to the planet. The circumplanetary disk is heated by the planet itself and any accretion luminosity from accretion onto the planet, but it's also seeing the full radiation field from the central star, no? Because it's a disk a circumplanetary disk that we put into a gap. And the second question, why is HD so important? So let me come back to this. HD is actually a molecule that has a very constant conversion ratio to H2. You know, with CO, we always have all these arguments out there, like CO is freezing out on the grains, and then it sinks to the midplane and gets transported away, and magically we have less CO emission than we think, and so we have a problem determining disk masses from CO. With HD, there's no chemistry involved, and so it's a very clean probe. I have to say that the caveat is still you need to know the excitation temperature, you need to know how to translate a line flux into a disk mass, and that's why I'm saying the best is to have both lines, because then you have a handle on the disk gas temperature, and that tells you how to convert HD line emission into disk masses.
All right, and then we have a question from Roy Van Bokel. So yeah, please feel free to unmute.
Hi Inga, thanks for the nice talk. Imagine you are looking at the PDS-70 system and are trying to see emission lines from one or maybe even two circumplanetary disks. Which line from which species would be best to go for, since this one is probably a lot cooler than the stuff in the planet around HD 100546, for example?
No, I'm not sure. I mean, you're still close to the planet, and these are very massive planets, like 10, 12 Jupiter mass planets. So they send out a lot of radiation to heat their gas as well. And there's still accretion heating going on onto the planet. So in that sense, no, I think I would still say CO is very robust. And next to CO, I would propose to look at water and OH as a next best. But to me, CO, because CO is also thermally extremely stable. I mean, it's the best molecule I think we have.
Okay, thanks.
Okay, and then let's see, on our Slack channel, we have a question from Walter Jaffe. So he asks, can any of the model codes handle time-dependent systems? You may also need a hydrodynamic subsystem.
That's a very nice question. Thanks, Walter, for it. Yes, indeed. One of the things we have done is we have coupled these codes, which are indeed snapshots, if you want, coupled them to a hydrodynamical code. So we use snapshot hydrodynamical density distributions in order to translate those into observables. The only time dependence we have in this code would be to just then glue snapshots together. And what we can do in a time-dependent fashion is we can follow the chemistry. So we don't have to have the chemistry evolve to steady state. We can say, well, let's inherit our chemistry from the molecular cloud, and then let's propagate it under the density and radiation field conditions in the disk further in time. But it's true. There is a big...
None of these allow feedback from the thermal systems to the hydrodynamics.
Yes. So yeah, I mean, one of the problems with the hydrodynamic codes is that they usually have a very simple energy equation for the gas. And our energy equation would be way more complex. So there will be a workshop in Leiden in summer, actually, where we will discuss how to bring hydrodynamics and these kind of thermochemical models together. But it's computationally challenging. And, you know, just to do it blindly for the entire disk, to me, sounds not the right way to go. I would identify what is really the problem and then see how do you decouple the different processes and what is the best approach to follow.
Well, I have another quick one if there's no other ones.
Sure, go for it, Walter.
Can you also handle X-ray sources at the center?
Yes, we can.
As well as, okay,
yes, we have X-ray radiative transfer, both with dust opacities and gas opacities.
Okay, very good.
And we can do AGNs, Walter.
Well, that's what I was moving towards.
That, yeah, Rovin Meiring did that in a paper a long time ago using exactly this code. Yeah.